The topic that we are going to discuss today is thermal energy store. Last time we discussed about how energy is transferred between kinetic energy store and potential energy store. Thermal energy store is a bit unique in this sense that energy from all kind of stores will try to move from those stores to thermal energy store. Whenever there is energy in any store of a body, except for potential energy, it will try to drift to the thermal energy store. How does this happen? For example, if an object has kinetic energy, it is moving, or it is moving in a fluid, or it is falling down. It faces two kind of forces. One is called drag force, and the other one is the upthrust force of the fluid. They both tend to transfer the kinetic energy of the object to their thermal energy store. So energy stored in a thermal energy store of a body is called thermal energy store, and energy from different stores transfers to the thermal energy store, or tends to transfer to the thermal energy store. One more thing about thermal energy store is that in the thermal energy store of any material, if we have different objects, say this is one block we have here. Similarly, we have a ball here or anything. This block is at minus 10 degrees centigrade. This is at 20 degrees centigrade. They both have thermal energy stored in their stores. Energy stored in their thermal energy store. So whenever an object we see all the material objects we see in our daily life, they have some energy stored in their thermal energy store always. Even if they are cold or hot, it doesn't matter. Thermal energy store will have zero thermal energy in it if and only if a material is at minus 273.13 degrees centigrade. That's a very, very low temperature, and when an object is at this temperature, then in its thermal energy store, the energy is there is no energy, that is zero energy. This letter theta here is representing temperature. So there are different factors on which thermal energy depends. That's why, like when I was defining kinetic energy, I said Ek. I did not discuss the change, but because every object has already the some kind of thermal energy stored in it. So whenever we are adding or removing the thermal energy from its thermal energy store, that means there is a change in the energy in the thermal energy store, or change in heat. So that's another name for thermal energy. Okay, so change in thermal energy depends on mass, time, specific heat capacity of the material, and change in temperature. So that's the property of thermal energy. If an object has some thermal energy in its thermal energy store, I will call it is at temperature T1, and when more energy is added to it, it will change the temperature from T1 to T2. If energy is coming into the thermal energy store, then we will say that T2, let's use the appropriate symbol that we have been using. Instead of representing temperature with T, let's just represent it with theta. So it is at temperature theta 1, and when the energy flows into the store, it goes on to temperature theta 2. So if the energy is coming into the store, then theta 2 is always greater than theta 1. But if energy is going out of the store, in that case, theta 2 will be less than theta 1. So that's the thing, that whenever thermal energy moves into the store, when the energy moves into the thermal energy store of an object, it will try to change the temperature. So change in thermal energy depends on change in temperature. So this is energy, heat, and this letter delta here is representing only the change in heat. Similarly, M is mass, C is specific heat capacity, and theta is temperature. So the thermal energy will depend on mass of the object, specific heat capacity, and change in temperature. The, uh, just for remembering this, whenever you see this letter, Greek letter delta written somewhere, just remember that whatever the quantity here, let's say A is a quantity here, it is saying that A final minus A initial. It is telling us about the difference between the two values. Okay, so whenever you see this letter, Greek letter delta, it means that you need to subtract final value from initial value. So it will be for temperature, and difference between the final and initial temperature, and difference between the final energy in the thermal energy store to energy in the thermal energy store before we transferred some energy in the thermal energy store. Okay, so that these are the factors on which thermal energy depends, and thermal energy tries to move to the energy from different stores tries to move to thermal energy store. Okay, so that was it. And then we already are familiar with the concept of energy. We already are familiar with the concept of temperature, and for at this level we can define the temperature by as that it is the degree of hotness or coldness of a body. It is the degree of hotness or coldness of a body. But if you want to divide it, define it further, you can say temperature is defined as the average kinetic energy of the particles of a system. At this level, we can simply say that temperature is the measure of the degree of hotness or coldness of a body. Is this clear? So that was about the thermal energy store. Now, in thermal energy store, we define a specific term which we called a specific heat capacity. So what is a specific heat capacity? Uh, let's just try to understand what specific heat capacity is. Specific heat capacity. So whenever we see different materials, they have energy stores within them. One of the store is thermal energy store. Now each type of the material has different capacity to store thermal energy. Like water, the thermal energy store of the water is very large. It takes in a lot of heat as compared to iron, whose thermal energy store is very small, and it takes very small heat in its. It can store very small amount of heat in its thermal energy store. So what will happen if the store or thermal energy store is full? Let's say if I have a material, this is a thermal energy store, and I'm pouring heat energy into this thermal in this store, and this store is now full of energy. So once the store is full of energy, what will happen? Once this store is full, the temperature of this object will be raised by 1 degree centigrade, and a new store, a door to a new thermal energy store will open, and now this store will be of the same size like this, and now this store will start heating thermal energy, start storing thermal energy inside it. When this store reaches its maximum capacity, the temperature will again be raised by 1 degree, and another store will be open, and that's how thermal energy is stored inside the material. So some materials, they have large size of their thermal energy store, and they can store more thermal energy as compared to some materials which have small thermal energy stores. But how do we differentiate between which material has a larger size of thermal energy store and which material has a smaller size of its thermal energy store? There is a way to find it. The way to find it is we take two different kinds of materials. Let's say I have taken iron a block of iron, and a block of aluminium. Both the blocks have the same mass, that is, mass of this block is equal to 1 kilogram, and mass of this block is also equal to 1 kilogram. Now I'm pouring in the energy in its thermal energy store. Whichever material absorbs more thermal energy to raise its temperature by 1 degree will have more specific heat capacity. So specific heat capacity means that how much thermal energy can be stored in the thermal energy store of a material without changing its temperature. The capacity or the ability of the materials to store heat energy, or the ability of materials to store energy in their thermal energy store without changing their temperature, is called heat capacity. And if we are saying specific, specific refers to one specific mass, that is 1 kilogram. So specific heat capacity will be the amount of heat energy stored by 1 kilogram of a material in its thermal energy store without changing its temperature. Or if you add further heat, its temperature is raised by 1 degree. So we need to be smart with our words when we want to define it. So what will we say? That specific heat capacity is the heat absorbed or stored in thermal energy store of a material to raise its temperature by 1 degree. So when will I know that the thermal energy store is full? When there is a change in temperature by 1 degree centigrade. So I'm pouring the heat in, and once the thermal energy store is full, the temperature, initially the temperature was, let's say, 25 degrees centigrade, and as long as I'm pouring the energy in its thermal energy store, the temperature start to increase, like 25.1 degrees centigrade, 25.2, and it keeps on increasing. When it reaches 26 degrees centigrade, and I am calculating how much heat or how much energy I have provided to its thermal energy store now. Once it reaches the 26 degrees centigrade, that much heat will be its specific heat capacity if the mass of the object is 1 kilogram. So that's how we can define a specific heat capacity. We go back to our equation and see if we can represent the specific heat capacity graphically. So we had that change in energy or change in heat, you can say delta Q or delta E, it's up to you, is equal to mc del theta. Okay, so we have delta E is equal to mc del theta, or delta Q is equal to mc del theta. From now on, I'm just sticking with this part because Q and E are the same. Q, when we say Q, it means that energy is in the thermal energy store. We are referring to the heat energy. Okay, so from this we can say, if I want to eliminate C, what will I do? Delta E is equal to m C del theta, and because I want to eliminate C, I have m multiplying on this side and del theta multiplying on this side. Is we are dividing delta theta on the both side of the equation. So dividing del theta on the both side of the equation will not affect the equation, and del theta is eliminated. So what I got is delta E divided by delta theta is equal to mc. And now I still got m. So what can I do? is I can divide the equation by m on the both side. So when I divide the equation by m on the both side, delta E divided by m delta theta is equal to mc divided by m. So m will cancel out, and we got c is equal to delta E divided by m delta theta. Or delta E divided by m delta theta is equal to c, which is the same thing. Okay, so delta E divided by m delta theta. Now we already know if you want to figure out the specific heat capacity from here, energy is measured in the unit of joule, mass is measured in the unit of kilogram, and temperature is measured in the unit of kelvins. So what will we get? C is equal to joule per kilogram per Kelvin. So from the units we can see that amount of energy absorbed by 1 kilogram to raise the temperature by 1 Kelvin or 1 degree is called specific heat capacity. So specific heat capacity C is, the unit of C is joule per kilogram per Kelvin, and that's how we can define J. And now you can actually find the gradient, and you can plot energy versus temperature, and from the gradient you can calculate your specific heat capacity. As we got our temperature on the x-axis, and we got energy on the y-axis, because these two are changing, but mass for m is equal to 1 kilogram. We got a specific mass, that is 1 kilogram. And now when I start raising the temperature, initially I see this kind of line, and then it straightens out like this. So we only consider this portion. That's because our experiments, usually these experiments, when we are finding a specific heat capacity, they have certain limitation associated to it. So that's why we ignore this portion. And now if you find the gradient of this plot, so you know gradient, that will be theta 1, and let's say this is our theta 2. With respect to theta 1 and theta 2, what we got here is delta E1 and E2. So change is E2 minus E1. So the gradient will be E2 minus E1 divided by theta 2 minus theta 1. And when you divide these, you get your specific heat capacity. So you can figure out the specific heat capacity of different material. For example, this is for iron, and then I got another kind of slope, which is kind of like this. Okay, and now this blue slope is for blue gradient is for aluminium. So for different materials you can find the specific heat capacity, and from the gradient you will know this should not be exactly like this, but a bit different. So let's say it's more going like this, and from this slope we try to from this gradient we find the specific heat capacity for different material. Okay, so that was about the specific heat capacity, but this is a very useful equation. Now I can manipulate this equation for different, because I can find energy with the help of this equation, I can find C with the help of this equation, but also I can exchange C and M and theta by doing the same steps. So if I need to find mass, it will be delta E divided by C delta theta, and if I want to find change in temperature, it will be delta E divided by MC. So that's how I can find my different variables in the equation. We got four different variables, and we can, if we got the three values, we can use them to find the fourth one. Okay, so that's how specific heat capacity connects with the thermal energy store